Hello, my name is Brock LaMeres and I will be your instructor this summer for EELE 371, Introduction to Microprocessor Hardware and Software. We also call this course Embedded Systems Design, which is probably a little bit more accurate, but we'll use the two interchangeably. In this video, I want to go over the logistics of the course, talk about how you log in, what you're going to be doing for assignments, how you're going to read and watch video, or read the book and watch videos, and how you actually are going to turn in the things that you'll be graded on. Before that, though, I'll give you an overview of why we take this course, why it exists, and then also a overview of myself and my background as the author of the book, the teacher, and also the voice and hands that you'll be seeing in the videos. So let's take a look at what this course is all about. So we are going to learn about computers. And so this class really is meant to give you a deeper understanding of the components in a computer and how they were used. But when we do it from a kind of a hardware or a level where the computer is already in front of us, what we're trying to do is we're trying to learn about a common architecture, and then we understand it more by programming it at a very low level. So we want to like write instructions for the computer and watch information move back and forth between memory and the CPU. Look at how things are manipulated. Look at how memory is allocated. And so we're trying to form an understanding of a computer. And this architecture that we learn is relevant to all computers. And so if you think about general purpose computers, laptops and workstations and servers, they all have the same general architecture. They have a central processing unit. They have program memory that holds your program. They have data memory, and they have I/O. And they all execute code in a very similar way. And so if we develop an understanding of just any type of computer, it applies to all computers. But in this class, what we do is we specifically start by looking at what we call embedded computers, also called microcontrollers. And these are the computers that you find them everywhere. These are the ubiquitous computers. So these are the ones in like your car and in your TVs and in thermostats and stuff like that. And the reason we do that is has many reasons. Number one, these type of computers are inexpensive. And so we can have a computer that sits in front of us, and that's what you're going to do, that we can actually program and actually watch it operate. And it doesn't cost, $1,000, right? We can spend $10 and have a little computer in front of us. And these computers, not only is that a good way to learn the architecture, which extends over to general purpose computers, but then we also get to learn about the type of embedded computers that are in everything, because there's more of these than there are of the general purpose. And so we actually look at this thing, they tend to call them microcontrollers because they're little computers that are embedded in a system that control things. And so what's unique about microcontrollers versus a general purpose computer is that it has a lot of peripherals such as analog to digital converters, serial peripherals, and a bunch of common interface peripherals that allow you to interact with the external world. So when you get done with this, what's cool about it is, number one, you learn about what a computer is. Number two, you learned how to program a computer. That's a good skill. And then number three, you learned about embedded computers and microcontrollers, which are the most commonly used computer anyway in the world. And so you have a really practical skill. Okay, so then here's how we're going to do it. We're going to march through 15 modules. This is a lot of modules. We're going to cover the entire textbook, but not all the modules are created equal. Okay, some are very short. Some of them are very long, and so don't worry, they're not evenly distributed, so don't worry about going, holy cow, 15 chapters. So for example, in module 1, it's only a couple pages long, and it's just to give you an introduction to what an embedded systems is and an embedded computer. Module 2 is going to be a digital logic basics. Now, this one, I want to warn you right away, you were supposed to have a prereq of digital logic circuits, okay? And so chapter 2 is massive, but it's supposed to be a review. So the way that you're going to approach module 2 is I would suggest going and just opening the homework assignments and then looking at what they're asking. And then if you don't remember anything, go ahead and access the resources I provide to you. But when you open the book and you look at chapter 2, you're like, holy cow, that's a whole course. And the reason it is big and it looks like a whole course, because it is a whole course. You're supposed to have taken that already. Okay. Then we're going to do module 3, which is just looking at the overview of a general computer and definitions and terminology. And then we get into module 4, which is where we look at the little computer board that we're going to have. So this is the specific microcontroller called the MSP430. and we're going to use the MSP430 FR2355 on this Launchpad board. And so this red board is what you're going to have plugged into your computer while you watch the videos and read, and you're going to type in example code and watch stuff, watch LEDs flash and do all this cool stuff. And then this is what you'll perform your lab on. Since we're going to actually be programming it, we have to start looking at how do we program. And we're going to start in Module 5 in a very low-level language, which is called assembly. Assembly is almost a one-to-one mapping of a line of code, a statement of code is an actual instruction that this microcontroller can execute. Very simple things like move information here, add in these two pieces of information, invert this word. So it's very low level. And guess what? It's a skill. So there's times in your career where you may need to program in assembly because it gives you very low level control of the hardware. All right, and then we go through, since we know how to, or as we're learning in assembly, we move through the three main categories of instructions, which is data movement, data manipulation, and program flow. And again, these three classes are implemented in all computer systems when you get down to the low level. Then we get to start looking at some peripherals, and so we start accessing the outside world. So Module 9, we're going to look at the parallel I/O system, which we just call digital I/O, and that's how you get information in and out of the system, of the microcontroller. Then we go and we look at the stack and the subroutines, which is how do you actually implement subroutines in a real computer, and then how do you dynamically allocate memory, which is using the stack. And then we look at interrupts in detail, and so all this is in assembly. And then we look at timers, and this is a very powerful peripheral that allows you to track time independent of the CPU operation. And we're still just doing this all in assembly, and it's low level, and we understand all the bits that we're banging. And then Module 13, we stop for a second, and we switch to C. So more than likely, if you program microcontrollers, you're going to be doing it in C. So what we do is once we have a basic understanding of what a computer is and how a microcontroller works and how peripherals work, then we switch over to C and we remind ourselves what C does, and then we actually implement everything that we've done up until this point in C. And you see how quickly you can actually implement these at a higher level language. And then that takes us into the final two peripherals, which are the most complex that we'll cover, which is number one, the serial communication peripheral, and then the analog to digital converter. So before we get into the logistics of the class, you must be wondering, well, who is this guy who's going to be teaching me? So I am a professor of electrical and computer engineer at Montana State University. So I am physically located in Bozeman, Montana. And I got my bachelor's degree from Montana State back in the 90s. And then I went to work for Hewlett-Packard, where I designed electronic test equipment for 8 years. And I was a digital hardware designer, so I did FPGA design, printed circuit board design, acquisition system design. And so all of the circuitry that I'm going to be teaching you about is stuff that I actually used as an engineer in industry. And so this stuff is real. It's not just make-believe. You will actually use this stuff. And so while I was working at Hewlett-Packard, I decided to go to graduate school. So I went to, I got my master's degree at the University of Colorado in Colorado Springs. And then after that, I started teaching as an adjunct instructor, classes on embedded systems at University of Colorado in Colorado Springs. And after a couple of years of that, I decided that I really liked teaching and I really liked being an electrical engineer and a computer engineer. So I decided to go back to school and get my PhD. And so then I continued working and going to school, but this time I was going to school at the main campus, University of Colorado in Boulder. And so then after years went by and I ended up getting my PhD, and that allowed me to become a professor. So in 2006, I came back to Montana State, and I have been a professor now for nearly 15 years. And what I do is I teach and do research in the broad area of computer engineering and digital systems. And so I'm showing you my website right here just to kind of highlight some of the things that I do. So the classes that I teach are like introduction to logic circuits, obviously, both at the very low level all the way up to senior and graduate level, digital system design and high-speed digital system design. And then I do research on, using embedded systems to solve problems and also coming up with novel computer architectures for various applications. So my main work, if I come out to my research over here, My main work has centered around trying to exploit these programmable logic devices to create real-time adapting hardware that can recover from faults or give you better performance in real time. And so most of my work has been funded by NASA. I currently have a project right now where I'm building a computer that's going to go to the moon in 2022. We actually have this computer that we've invented called RAD-PC that uses an FPGA and can react to ionizing radiation that causes a normal computer to crash. And so we've developed this computer and we're going to fly it, or we actually have 2 small satellites in orbit. One of them is called RadSat-U. This is a picture of it right here. This is its launch back in November of 2019. I'm standing in this crowd right here with my students watching that go off from Wallops Flight Facility. Here's a picture of it being pushed out of the International Space Station, so it's in orbit right now. We have a second satellite that's up there called RadSat-G, and these things are about the size of a loaf of bread. Here's its pictures of it. It's launched at night, being pushed off the International Space Station again. And then we do all sorts of other things like balloon flights to try to test this computer in various environments. We've had it on the International Space Station. Here's a version of this computer, RAD-PC, being installed by an astronaut. And then we've done everything from flying on sounding rockets to weather balloons. And so anything and everything to just kind of test that technology. So what my background brings is I have a degree, a PhD in electrical and computer engineering. I've also worked in industry using this stuff. And then I also do research that really takes what I'm about to teach you and actually implements it in applications that can kind of advance computing technology. Okay, so at this point, we're ready to look at the logistics of the class and how you're actually going to learn and do assignments. So it all starts with this learning management system called Brightspace. This is the course website. And the address is ecat.montana.edu, and it'll redirect you to like ECAT1 or ECAT2, but just ecat.montana.edu is all you need to remember. And you're going to log in with your net ID and login that you use for everything else and that was assigned to you when you applied at MSU. And when you come in here, you're going to see the Brightspace main page. And what you'll see is that over here on the bottom right is your courses. So you'll see microprocessor, hardware, and software systems. And then I have an announcement on here just to kind of show you that you're in the right spot. So if you go ahead and click on this, you're going to come to the course shell, or the course site for our class. And so here you are, you get like, oh, ones and zeros, and you kind of you see that announcement. I put that there so that you can, you're in the right place. And when you come in here, what you're going to notice is that there's all the tools available to you through Brightspace up here at the top. What I do is I put everything in content and link it to a page for each module. So if you come here, you can either click right here to go to the first page, or you can come up here to content. So if I click on content, you can see everything in the class. There's really only 2 folders. There's course activities and data sheets. And so if I look at course activities, you're going to see kind of an information syllabus page, and you're going to see a page for every single module, all 15 that you're going to work through. And so you're just going to march through these deliverables. Data sheets, if you click in there, you're going to see the 3 primary data sheets that I refer to throughout the class. The users family, which I call the monster, the device specific, and the board specific. And all that will make sense once you start working through the activities. So if I go into course activities and I go to course information and syllabus, you start to get an overview of the class. Now this page is just a quick summary of the syllabus, but I do it so that you can have some links to things. So for example, right here, you're going to see a link to the syllabus. So if you click that, you'll see the detailed syllabus, and we'll come back to that in a second. And then you come down here and you see your contact information for myself and for Stephanie Smith, our teaching assistant. Now we're going to use email as our primary mode of communication, and so one of the things I do is I encourage you to try to email in a professional manner. And so much so that I have this professional email etiquette guide. It's a little PDF you can read, and if you read through that, and at the end of it, I give you an example email to send to me. And I'll actually give you extra credit if you send me an email using the preferred format given in that etiquette guide. And so I'll actually give you 20 extra credit points, which is 2%. So I'm going to give you a 2% credit bump, which could mean the difference between A and a B, as long as you just read through this and send me an email. So you can do that right away and start building up your account balance. Coming down here, the required material, you need a computer with internet, okay? And this class is unique in that you do have the ability to run on a Mac, which is very rare in engineering. Almost always the tools for engineering run on Windows or Linux only. So this is one of the few classes where you can use a Mac to run our software that we're going to use to program the embedded system that we look at, or our MCU. That you needed the textbook, but luckily for you, we are pre-publication, so I'm actually going to give you an ebook version of the textbook. So you can download the textbook right here. It's a monster. It's 115 megabytes, but you don't have to buy a textbook for this. And you need a portable lab kit. And so at this point, you should have emailed me your address, and I should have already mailed you a kit. But if you haven't, you should go find your emails that you haven't been reading and make sure that you understand where they are, because that's the address I'm going to be sending to you. And you should also let me know if you're going to pick this kit up or if you are going to have me ship it to you. Now, luckily in this class, the first lab is not actually going to be due the first week. It'll be due Tuesday the second week. And so we'll look at the deadlines on that. So you do have a time. We can get you the kit during week 1. And then you need a camera capable of taking short lab demos. This is usually just your smartphone. So that's how we're going to demo the labs. Okay, so let's go ahead and look at the syllabus and look at the more detailed. So this is kind of like the written syllabus, the formal syllabus, and it has all the same information on here. This is a 12-week fully online class. There's the requirements. You need to have a digital logic prereq, okay, like I mentioned before. So if you don't have that, I've pretty much checked everybody's prereq, and I think everybody does. But if you don't, you're going to run into that immediately in Module 2. And here's going to be now finally what we're going to be doing. So you are going to be graded on homeworks, labs, and a project. Okay, and that's it. There's no real exams. There's just, you're going to do a bunch of homework, you're going to do a bunch of labs, and you're going to do a final project, and that's it. Academic policies. So this is the whole don't cheat thing. So there's a difference between cheating and collaboration. In engineering, almost all problems are solved by collaborating. So there's no such thing as working on your own. So it's, if you are around other people that are in this class, you can certainly collaborate and talk to each other about, you know, the labs and the material. The difference between collaboration and cheating is when you turn in somebody else's work as your own. Okay, so you're working together, that's fine, and then all of a sudden you go, I don't have time to do this assignment. Can I just use your file and I'll upload that as my own? That's when it becomes cheating, and that's when we have a problem. Okay, so don't cheat. But you're encouraged to collaborate if there's somebody to collaborate with. All right, so the course components are going to consist of this. You are going to read the book and watch instructional videos. And the way that I did this is the book, the videos match the book exactly. So you can, some people like to read, some people like to watch videos. You can do both, you can do either, but it's the same information, okay? So that's how you're gonna get the knowledge into your head. And then what you're gonna do is every section of the book, or every section that is covered by videos, has a multiple choice homework assignment. And there's a lot of these. There's 51 of them, but they're relatively simple. It's just really to make sure that you understand the key points from this section that you're covering. And then there's a lot of these, but there's lab assignments that are going to be relatively short labs where you are assigned to do something on the MSP 430. That's the MCU we're going to use. And so you're going to do something, and then you're going to demo it, and you'll get graded on that. Now, to demo, what you're going to do is you're actually going to take a short video of your board, your little Launchpad board, and it's going to be blinking LEDs, or you're going to take a video of the Code Composer environment. That's our development environment, and you'll know exactly what I'm looking for. But what I want each video to basically just start the thing, show a picture of your face and say, hey, this is Brock LaMeres, I'm demoing lab 2.1, and then show me the assignment, okay? And so you're gonna upload those and try to make them short, 5 to 10 seconds is the most we really want. If you wanna upload it to YouTube, that's fine too, and then just upload the link. But every time you do a lab, you're gonna have to upload a video showing you did it, and then your source code, and then later in the semester or later in the session, we'll have measurements that you do screenshots of. And then we just do a bunch of those, okay? And then at the end, you're gonna do a little project, and it'll be more open-ended, and you'll get to kind of decide which project you do, and that'll pull everything together. Okay, so now here is the big schedule. So every time that you log in, I suggest you look at this schedule, okay? So this gives you every single assignment and activity that you're gonna do, how it's graded, how much it's worth, and when it's due. So in general, what I do is every week has deadlines that are due the following Tuesday at noon, okay? And so for example, digital logic basis computer systems, you can see that they're due next week or the following week at noon on Tuesday. But I need you to get going, and I need to know that you can log in and do an assignment. So what I'm going to have you do is I'm going to have the first multiple choice homework be due the first Tuesday. So it's like right away you got to have this thing. And that shows me that you're alive and kicking and everything's good. Okay, so you can look at all these, and the way that it works is when I say it's a section or topic, it's 1.1. Those are sections in the book. Okay, so the first chapter only has one section, but let's look at like, for example, chapter 3. There are 3 sections: computer overview, computer hardware, and computer software. Each one of those you have to read or do and watch videos, and then you're going to do a homework on that material that you just learned. And the homeworks are multiple choice quizzes. So then you're just going to boom, knock out that section, understand it, then do the homework. Next section, do the homework. Next section, do the homework. But notice that all these deadlines for the week are due the following week, Tuesday at noon. And the reason they're due at Tuesday is I want you to be able to have the weekend to do it. And then I want to be able to give you a day like Monday in order to ask questions from us. And then I never want a deadline outside of work hours. So between, let's say, 8 and 5, if I give you a deadline at midnight, everything's going to go wrong at midnight, and there's no chance that you can get a hold of us because we're sleeping. And so I don't ever want a deadline that's not outside of a working hour, so that if you have an immediate problem, I can respond to you. Okay, so that's the rationale for that deadline. As you go down with the first, when you get into week 2, we'll actually have our, well, actually there's a lab 1.1 that just shows you how to get the CCS running through Code Composer Studio. And so what you'll do is you'll upload, the deliverables. But then as we move through the material, you'll start noticing that there's more and more labs. So once we get to like week 3, you notice that we've got 7 sections, and it looks like this. You go section 6.1, 6.2, 6.3. There's homework, homework, homework. Then you do a lab. Then it's 6.4, 6.5, 6.6, homework, homework, homework. Then you do a lab. Then section 6.7, and then a lab. And so this gets into the flow of kind of how we're going to do it for the rest of the semester. And you notice that it's just like, it just keeps cranking and cranking and lab and lab and lab and lab and lab. Homework lab, homework lab, homework lab, until you get to the end. And then the last week we have a little final project. And so that's it. And we work through every chapter in the book, every section in the book that has a homework. There's a lot of homeworks. There's like, there's 51 homeworks, I think, and then there's like 20 something labs. So there's a lot of this stuff, but it's designed so that they're not, one lab is not like 8 hours. Okay. It's like a lab should be 20 to 30 minutes type thing. So they're small labs, but there's a lot of them. Okay. All right. So that is going to be the schedule of the course that we have. I mean, that is it. and let me wrap up with giving you a little bit of guidance on how to succeed in an online environment, or this online environment. So first and foremost, you're taking a 4-credit class spread out over 12 weeks. And what I've found historically is that this takes about 10 hours a week. And so what you should do is you should plan on allocating 10 hours a week. Sometimes it might be more, sometimes it might be less, but that's on average how long it's going to take. I highly recommend that you log into Brightspace and make progress on the course 5 times a week. So I've found that is the optimal number of logins. So you should break that 10 hours up into 5 2-hour sessions. What I'm really discouraging is don't wait until, Monday night and try to do the entire weekly activities, starting at 7 p.m., right? And then just do an all-nighter. That's the worst way to learn. The best way to learn is to do a little bit and then sleep, and then a little bit and then sleep, and then a little bit and sleep. So the magic numbers here are it's about 10 hours a week. Shoot for 5 logins every week. The next tip I'll give you is to check your email. Okay, that is how I'm going to communicate with you. That's how you get help from us or initiate help from us. If we need, we will do video calls with you and look at what you're doing. You'll be shocked at how easy we can find errors in your code if you email us your code. It just comes from looking at these assignments for years, and so you'll be shocked at how easily you can get help. But remember, you contact us, and then if we can't help you, we'll do a video call and get you going. And then finally, this is key: don't stay stuck. Okay, so you need to. You're assuming you're working on your own. You're going to be sitting there working through weekly activities. Okay, so you're sitting here and you're like, okay, I've got my weekly activities. I'm going. Every week you look at this thing and you know what you're supposed to do for the week. You know the progress you're supposed to be making, the sequence you're going to be making. And the key here is to know where you're going, know what you're working on, and knowing if you make progress. And so the worst case scenario for online learning is where you get stuck and you're just staring at something for hour after hour, and you start thinking, maybe I just need to stare at it for longer. And then it becomes 2 hours, 4 hours, 8 hours, and you're not making progress. I recommend that if you're stuck on something, and what I mean is stuck is like you're not moving forward, you're not progressing for more than 30 minutes, then you need to stop and do something else. Okay. This is a lot different from you're working on the weekly activities and you've been working for a half an hour and you're making progress. You know that you're working through the videos, you're understanding homework and you're going to the next thing. That's making progress. I'm talking about you're stuck. You are just sitting here staring at your code and nothing's happening. If that happens for more than 30 minutes, stop. Get up and do something else. Go exercise, go to sleep. If you're really stuck, you email us, okay? But don't be stuck for longer than 30 minutes. And just rebooting your mind will allow you to come back and start fresh, and that'll help you kind of make progress, okay? So this is all about miniature goal settings, knowing where you're at, knowing if you're progressing, and that's how you do this, okay? I want you to immediately embrace this culture where you are not alone, okay? So you have a teacher, me, and a teaching assistant, Stephanie, who are working here full-time for you, and we're available to help. Now, it is online and asynchronous somewhat, meaning that if you email me, it might take an hour or two to get back to you, but that's fine. Maybe that's time for you to reboot. Okay. So don't stay stuck. All right. That is it. And at this point, you are ready to begin Module 1. You're going to go to the Module 1 webpage and you are going to look at the activities. You'll say, oh, I'm going to read the book, section 1.1. I'm going to watch the video, or I just do one or the other. I'm going to do the homework here, and I know when it's due, and then I start working on the lab, and I know when that's due, and I just start cranking. All right, that is it. Good luck with the course, and I look forward to working with you this summer.